Okay, so today I will start with the fundamentals of linear models and the problem of estimation. So that's the first topic we'll do linear models. What we consider is we'll consider linear model, define it precisely, and then discuss estimable linear functions. Okay, that's what we're going towards too. So make this white. So we will discuss today linear models. So I'll define precisely what a linear model is. And then I'll discuss the problem of estimation given a linear model, what's estimable and not estimable. And then if I have time today, I'll close off with least squared estimation. So that's the plan for this week. Very nice. So let me begin with a particular model, and let's discuss a few things about the model specifics, and then carry on. So let me call this model 1. So let's consider the following model. The model is the following. So I have random variables indexed by I and j, yij. So that will be equal to some fixed parameter mu plus some mu I plus some errors. Errors I'll define it as epsilon ij. So so let's say I runs from 1 less than equal to I less than equal to k. So keep this k in mind. So I'll mark it in pink so that the k is fixed. And I let j run from 1 to ni. So ej runs from 1 less than equal to j up to some ni. This is a very general model. So I have I've explained to you what these parameters are, what mu is, what mu I is, and epsilon I is. So first things off, mu and mu I are given real numbers for every I between 1 and k. Okay, so 1 less than equal to I less than equal to k, mu I is a real numbers. What are epsilon ij? Epsilon ij are what I will have them follow normal with mean 0 and variance sigma square. Okay, and independent. So they are IID normal with mean 0 variance sigma square. This is again true for everybody. So all the i's from 1 to k. Let me copy it. Let me paste it here. And all the j from 1 to ni. Very good. So that's epsilon ig. So the way you think about this is that you think of the I as indexing populations. Okay, so you think of I as indexing. So you think of I as, so this population 1. So then you have population 2. And then all the way up to population k. So the I indexes the population. Okay. And what are the yij's? They are characteristics of the population. You can think of them as with various attributes of ni attributes, right? So you'll have, so what will happen is in the population, let's call it population is k. So k is like in different color. We'll put like this. And what I'll do is each population will have characteristics. So this y11, right? y12, and all the way, let's say, till y1n1. That's what y1 is. Then let's say population 2 has data set like y21, let's say, and y22 all the way to, let's say, y2n2, which is a little bit larger than n1, let's say, and yknk somewhere. So yk1 all the way to yknk. Maybe yknk is a little larger, so it'll go all the way down here. So let's call this as yk2. so on to yk, nk. So that's your data set. And your data set is distributed as normal with mean mu plus mu I, each random variable, and variance of the random variable epsilon square, sigma square. Right. So let's again fix one last notation. Let's figure total size. So let's call that n. N is just n1 plus n2 plus n3 all the way up to nk. That's the total sample size. So let's call that as the total sample size. So you've gone to each population. You've gone and sampled n1 from population 1, n2 population 2, and nk from population A, and collected attributes y1, yij's. And our basic assumption is yij's behave like mu plus mu I. So mu I is sort of the ith effect of the ith population. Mu is the overall effect in some sense. So here are some questions. So let me write the questions down. So the question is, so here are some questions in estimation. Can we estimate mu? Okay. So from the yij's, right? And if yes, what is the estimate? Right? So if yes, and if yes, what is the estimate? Then what is the estimate? Right. Let's say estimate of mu. This is one thing I must think about. So the first question, it's called the first question. The second question I want to address is the following. Can I estimate instead of mu, so the model has mu, I have mu plus mu I. Can I estimate mu plus mu I? So can I estimate mu plus mu I? And if so, what will the estimate be? Right. So question mark on both sides. So every given I want to estimate mu and mu plus mu I. Then suppose I want to compare between populations, because mu is the overall effect. Can I estimate mu I minus mu j? So can I estimate mu I minus mu j? And if so, what will the estimate be? And here I will think of it just to make sure that I don't do any sort of silly things. I'll think of I not equal to j and I and j between 1 and k. Very nice. So these are some of the questions one needs to understand. So let's go back to the thing. So mu is the overall effective mean in some sense. It's common mean to everybody. Mu I is the individual guys, and epsilon ij is the normal random variable with mean 0 and variance sigma squared. That makes yij governed by this mean and variance sigma squared. Right. So now I have k population. So now I can understand many things in population. One is, how does the population vary within group? How does the population vary across groups? And what is the overall variation as well? So there are three things one can consider in this data set. So let's define these statistics you may have seen in your earlier classes. So first thing we will do is we will decide how to quantify within group variation. Okay, that's the first thing. So let's do. So first thing is, I'll try to understand within group variation. Okay, so what is this? This will take the variance of group I, right? This is the variance of group I. So let's write this down. So this is essentially, this is the variance of group I and how can it be approximated by? An estimate for this is just the sample variance. So let's do that. So the sample variance is going to be what now? So I will take 1 over ni minus 1. I will take the sum from j equal to 1 to ni, and I will take the yij minus yi bar, right? That's I'll just take the mean of the yi. So I'll just yi dot. So I'll vary yi bar and whole square. So where yi bar is, dot bar is 1 over ni summation j equal to 1 to ni of yj, right? That's what yij. So this is well known, right? This is so variance group of group I we know can be estimated by, we know this is called the sample variance, right? Sample variance. I mean the ith, so this is ith group sample variance. Very good. So that's one way of understanding one estimate of variation in group I. Very good. So, and also I don't know if you remember your earlier classes, that this is like an unbiased estimate, that its mean is the true variance in group I. It's an unbiased estimate. And it's from population I. Okay. The next thing one can do is one can also understand this from the data set. It's called the sum of squares within. So I'll call that sum of squares within. So these are all important quantities. I will come and discuss their significance as I go along. Sum of squares within. Right here, what I do, I do the same thing. I do SSW. So SSW, sum of squares within, is defined as, I will just take the sum of all the groups I equal to 1 to k, and I will take the sum from j equal to 1 to n sub I for each I. And what I'll do, I'll just take the yij and subtract y bar I dot, the whole square, just like I did before. I won't divide it. I'll just think when I just sum of square. Then this is all. These two things will classify these two ideas. Maybe I'll just call this in pink so that I don't sort of needlessly sort of confuse you with another label. So these are two quantities that are typically within group variations one can do, and sum of squares within is just the entire overall groups. Now one can do between group variations, right? So let's do that. Let's do between group variations. So between group variations. So how do I understand that? So I have to go across groups to understand what the between group variations are. So for this, there's something called sum of squares between. So I'll call that sum of squares between. So sum of squares between. So that's like SSB. I'll call SSB. So I equal to 1 to k, the sum from I equal to 1 to k. So sum of all groups. And then what I'll do is I'll just do the ni. And within each group also I'll take the mean. So I'll take the yi dot bar minus the overall mean. So I'll call this the dot bar whole square, where y dot bar is the entire mean. So it'll be 1 over n, the sum over I from 1 to k, the sum over j from 1 to ni of y sub ij. Right. So now, of course, statistically speaking, they are sort of very, very interesting random variables. we'll try and understand the distribution in a second. So what I want to close with is a couple of observations. Let's go there. So what are observations I want to make? The first observation I want to make is the following. See, if I take the sum of squares within and add sum of squares between, so sum of squares within plus sum of squares between, so I take the two sum of squares, this is why I call them and I define them. So the first observation, what will this give me? So it'll give me, if you look at it, if you go back up, so sum of squares within is this. Let's copy that, sorry. Right, let's copy that, let's bring it down. The sum of squares within. And then to this, I add the sum of squares between, right? So sum of squares between, that's plus this person right here. That's what I have, right? So now I can do a little sort of trick here. So this is equal to. So I have the sum from I equal to 1 to k. I take the first guy, copy it, I place it person here. That's from between. That's right. I'll do this, right? Then I put a bracket around it. So that's for each I have a sum from j equal to 1 set, and I have this. And this person, these ni people are here, I put them one in each bracket. So same as taking this person right here, I copy it and I paste it right here. Plus, and I close the bracket on that side. Right. So all I did was let me just mark this in pink so you can see the sort of the difference. So all I did was I just put the ni's into each sum, and that give me y plus y whole square. Right. So this, if you think a little bit, just look around a little bit. So what is giving you this is just same as the sum from I equal to 1 to k, right? Sum from j equal to 1 to ni. And if you expand and contract the sum, all you'll get is the whole thing is just yij minus y bar dot whole square. Because the cross terms will vanish, and this is exactly what you get. But what is this now? This is just the total sum of squares. So in some sense, we have divided the sum of squares within and sum of squares between. If you add them up, as you should get the total sum of squares. Right. One observation. So I don't know if you have seen this in statistics as the epsilon ij's are all independent here in the first line. Let's go first line. They're all independent, and so the y's are all independent variables. So if you look at the sum of squares within and sum of squares between, you can actually show by using standard methods that this is a nice observation to do. I'll leave the exercise. If you have not seen it before, just try and do it. That the sum of squares within is independent of sum of squares between. This is one observation you can check. Okay. So I will not show it in this class. Maybe if you have not done it before, just send me an email and we can cover it in the next class. But as of now, we will leave it at this point. Number 3 is nice observations. Now, so these are all sum of squares, right? So sum of squares where each of them is normal, right? Each of these is normal. So these are all normal random variables. So square of normal is chi-squared. So this you can clearly show. It's not hard to show again. It's another exercise. The sum of squares within is distributed as chi-squared with k minus 1 degrees of freedom times sigma squared. And sum of squares between is distributed as chi-squared k minus 1, sorry, k squared n minus k, the other part, n minus k sigma squared. And the total sum of squares is distributed as chi-squared with n minus 1 degrees of freedom, which is addition of the both, times sigma squared. So one thing you can observe is that the degrees of freedom varies across each of them, right? Right. So let's make it a little smaller so I can put everything to one side. So let's bring it here. Right. Let me make this across. Let me make it a little smaller. So here the degrees of freedom is, let's mark it down. It's k minus 1. Right. I copy the same thing and I bring it down here. The degree of freedom here for this sum of squares between is n minus k. Right. And the same thing, sum of squares, total sum of squares, the degrees of freedom is n minus 1. So significance of this you will see as you go along why this is the case. But so this is the total. So in some sense, if you notice, this plus this gives the total degrees of freedom. So sometimes people write the degrees of freedom for SSB, SSW is this, for SSB is this, and degrees of freedom for total is this. Very nice. So there's sort of a, so let me just go over this one more time so that we sort of get a handle on this. So let me just see this is correct. Let me go back here, 1 Feb 9 for you. So let me start from the beginning, come back slowly so you can see the double page. So we started with a linear model that was just a basic model we defined. So here yij's were just mu plus mu I plus mu I plus epsilon ij. So simple model I defined. I haven't told you why this model is important. We'll come to it slowly in a second. And then the questions I asked was, can we estimate mu I, mu plus mu I, and mu I minus mu j, sorry. And then I went on to define within group variations by two quantities. One is variance of group I and sum of squares within, and between group as sum of squares between, right? And once I had this, I made the following observations, that if you add these two people, you'll get the total sum of squares, right? And it's an interesting statistical fact that sum of squares within is independent of sum of squares between, and the distribution of each of these quantities is of the sort. So why are these distributions relevant? Because we know on this side, we know the yij's are normal, and SSW and SSB are sum of squares of normal, which are like chi-square. Very good. So one last thing I'll do in terms of notation, and then I'll try and come back to in the next video. I'll try and tell you how to play with the model. So first thing you observe is in the above model, what are the parameters? So the parameter vector. So I'll fix notation. For the above model, the parameter vector is, let's call it as beta. What all parameters were there? I had the mu from the first guy, right? Then I had the mu I, that is mu1 for the first guy, mu2 for second guy, and so on and so forth, up to mu sub k. This is what I had, right? So this is the parameter beta, which you do not know, is an rk plus 1 vector. Then I had a design matrix. So I'll call this a design. This is the parameter vector. Then what I'll call the next notion is design matrix. Here, this is an n cross k matrix, which is such that the expected value of the vector y, the expected value of vector y, is going to be equal to x times beta vector. Okay, that's what the matrix X does. Right? But what is y? Where y is an n cross 1 vector, each y tilde, such that, so it's a data vector, and how will I write it? I will write it exactly like this. I'll write it as y11 all the way till y11, y1n1, right? Then I'll have y21 all the way till y2n2, and I'll go all the way till yk1 till yknk. So I'll write the y as one long vector. So if I want this, what will it will force x to be what given what y what let me go copy what yij's are from we go back all the way up to what the yij's were. So yij's look like this, right? This is what yij's look like. So we copy this down. So I keep it for myself. So I want this, right? We want this. Let me paste this. Let me make it smaller. Let's say red. This is what we want. So epsilon i's have mean 0. So you want x to be, so to achieve this top line, if you want to achieve this line, then here y is this, you force your x, like if you do a standard matrix multiplication, you force your x to be what? The first row will be 1, 1, that is mu1, mu1, 1, everything has to be 0. The second row will be again 1, 1. So you'll have n1 of these guys look exactly like this, right? So let me call this as, let me move this across a little bit. So you'll have n1 of these guys like this, right? And then n2 of the guys will look like the next will be 1, 0, 1, 0, 1, 0, 1, 0. So that will be the n2 guys, right? It will look like this. Look like this. And so on and so forth. And all the way up to nk guys. Next n3 will be 1, 0, 0, 1, and so on and so forth. This is how the x will look like. And what will this happen? This will make the model. So therefore, if you want this particular model, such that the mean is x times beta, what we achieved is that this for 1 less than equal to I, less than equal to k, and 1 less than equal to j less than equal to ni, you will get y is equal to x beta plus epsilon. But what epsilon I'll do, so I'll call y tilde and x beta, epsilon tilde, where epsilon tilde is equal to, I'll just write the same way as I wrote y. So I'll have epsilon 1, 1, epsilon 1, 2, all the way to epsilon 1 and 1. And then I'll start with epsilon 2 and 1, all the way to epsilon 2 and 2, and all the way to epsilon k and k. That's what I get. Very cool. Let's stare a little bit. So this is one way of doing this whole thing. You can design a parametric thing and do it. So this object here is called the linear model, y equal to x beta plus epsilon. So there's one quantity x here, this is y, so this is x, this is y equal to x plus beta, and y, the vector y is given by this, the vector beta is given by this, and the vector epsilon is given by this. So our model can be written as y equal to x beta plus epsilon.